I believe we're live.
Okay, great. Hi, everyone. Welcome to the Machine Learning and Data Science Talks. Our session today is with the speaker talk titled PyNNDescent, Fast Approximate Nearest Neighbor Search with Numba. Leland?
Thank you, Fatma. So PyNNDescent is a library for fast approximate nearest neighbor search. So before we start, what do we even mean by nearest neighbor search? So suppose we have a bunch of data points, probably as vectors, and a defined distance measure between the points. And now suppose we get a new point that's a query point in orange there. The nearest neighbor search problem is to find the point or points in the original data that are closest to the query point with respect to that distance measure we had. That is, its nearest neighbors. So why would we want to find nearest neighbors of a point in a vector space? It turns out that a lot of machine learning algorithms rely on nearest neighbor computations at their core. Being able to do nearest neighbor computations efficiently can make a huge difference to the performance of these algorithms. There are obvious things like k-nearest neighbor classifiers and k-nearest neighbor regressors, but as you move into unsupervised learning, you have a lot of clustering algorithms that have efficient implementations that require good nearest neighbor search. And the same is true of a number of different dimension reduction techniques. Often the nearest neighbor search, particularly for high dimensional data, is the bottleneck for these algorithms. And there are also entire classes of recommender systems and query expansion methods built on top of efficient nearest neighbor search. That explains why finding nearest neighbors might be good. Why use approximate nearest neighbors? It turns out that computing exact nearest neighbors is very, very expensive. If you're willing to allow a little inaccuracy, not always finding the closest neighbors, you can get a massive, as in orders of magnitude, speed up in nearest neighbor search. So now that we've established that finding nearest neighbors is going to be useful, the next question is, how do we do it? The obvious approach is to simply compute distances to everything and take the top ones. But that's going to be very expensive, and we want something better. The classical approach for something faster is to use space tree structures. We'll cover this very briefly just so we can get an idea of the challenges of this sort of approach. The core idea of space trees in general revolves around hierarchically partitioning the space into ever smaller cells. Then, when searching for nearest neighbors, you can search down through the tree structure and use the nearest neighbors found so far, bounds on the cells, and the triangle inequality to eliminate entire branches of the tree from being searched. An example of this is a KD tree, which cuts the space into boxes. This only works well for certain distance measures, but it's very efficient at bounding things when it does work. A downside is that as dimensionality grows, bounding things into boxes is tricky, and the bounds on the boxes get worse to the point where instead of order log n queries for low dimensional data, it starts looking a lot like brute force for high dimensional data. A ball tree is another example. It solves the distance measure issue by using the distance measure itself to draw balls that carve up the space. This is a lot more flexible, but the bounding isn't as good, and it gets it worse at least as fast as KD trees. A solution that adapts better to the intrinsic dimensionality of the data rather than the ambient dimensionality, which tends to break those earlier tree approaches, is a random projection tree. Here we carve up the space with random hyperplanes. A downside of this approach is that we don't get any bounds on the cells. We just have to search down to the leaf of the tree and see if the nearest neighbors are there. If they happen to be on the wrong side of a hyperplane, we're just going to get the answer wrong. This makes random projection trees an approximate nearest neighbor method. You can decrease the error by building lots of trees and trying all of them, but the number of trees required to get good accuracy can tend to grow very large. Newer approaches to nearest neighbor search often use graphs instead of tree structures for the search. Since this approach is at the heart of PyNNDescent, I'll spend a little while explaining some of the details and why it works well. So, how do you use a graph for nearest neighbor search? There are a number of papers that have variations on this. The starting point for me was a paper by Dong, Moses, and Lee from 2011 on nearest neighbor descent. There's also a great paper on a different graph-based approach called HNSW by Malkov and Yashinin. And there are great papers from the NGT library by Kawasaki and Miyazaki, again, using graph-based search techniques. There are lots more papers on this, but I think these are the primary references that provide a good starting point if you want to get into this topic. So the key is to start with a nearest neighbor graph, or something like it, where each node is a data point and it has edges to its k nearest neighbors in the data space. Now, assume we have a query point and we want to find the nearest neighbors among our training data. To get started, we'll choose an initial node in our graph, potentially just randomly, and this will be our candidate node. So here's a nice pictorial example of this for two-dimensional data with Euclidean distance. The candidate node is in red, the graph node in blue, the query point in orange. Now, we're going to look at all the nodes connected by an edge to the best untried candidate node. Now, since we're just starting here, there's only one candidate node, but we'll come back to that. And then add all those nodes to the candidate pool. So that's going to look something like this in our pictorial example. We started with our candidate node. We're going to add all the nodes connected to it. If we keep doing this, we'll end up with a lot of candidates in our pool. So we'll sort the candidates by distance to the query point and keep just the k best candidates that are closest to the query. That would look something like this. The green nodes are our sorted list of candidates, and we've truncated away that one gray node. But now we have a new ranked candidate pool. So we can go back to our expansion step and expand the best untried candidate node. When there are no candidates that we haven't already tried, we've gone as far as we can, and we can declare ourselves done and return the candidate pool as the k nearest neighbors of the query point. So we can see this in an animation working its way through the graph. It's going to add in the points, sort them, and then work from the next best untried candidate, and so on, slowly crawling through the graph, getting closer and closer to that query point, eventually arriving at the two closest points. Now, that didn't look so great. We tried almost all the nodes in the graph, but it turns out that's just an artifact of the small size of the graph. On larger problems, it looks a lot better, and as you scale up, it gets better still. So here's an example on a large graph, and even with a worst possible initial candidate starting in that top corner, we find that we're just crawling through the graph, computing only a small number of distances. We're only computing distances from any of the gray points there, and we still find the nearest neighbors of our query point in orange. A catch with this approach is that we can get stuck in local minima here. So this is only ever going to be an approximate nearest neighbor search. But the best part is that since we're walking in a nearest neighbor graph, this scales extremely well with the ambient dimension of the data, as long as the intrinsic dimensionality of the data is lowish. And this is in stark contrast to all those tree-based methods, which really struggle with higher dimensional data. So that's how we find nearest neighbors of a query point given a nearest neighbor graph. But to build the nearest neighbor graph, we need to find the nearest neighbors of all the training data points. So how do we do that nearest neighbor search? It turns out we can actually sort of use the algorithm we just described. We can run the search on any graph. It doesn't have to be a nearest neighbor graph. It's just that it'll work badly and have a much worse chance of finding the nearest neighbors on a less good graph. So we can always just run one iteration of the search, expanding out to find the neighbors of neighbors as new candidate neighbors. That won't work very well, especially if we start with a random graph. But sometimes we'll find better neighbors. And so we can update the graph. But then we have a better graph, and we can run another iteration of search on the better graph and have a better chance of finding better neighbors. So if we start with a completely random graph, we have essentially no neighbors correct, just 1% accuracy by pure chance. After one iteration, looking at neighbors of neighbors and updating our neighbor lists, whenever we find better neighbors, we end up getting a lot better graph. Another iteration, searching on that new and much improved graph, and all of a sudden we've leapt ahead. We're already at 95% accuracy for neighbors. A third iteration, and we get to 99% accuracy. But we do start hitting diminishing returns now because most of the neighbors are already correct and there's very little room for improvement. A fourth iteration makes things a little better, but more iterations will fail to provide any further improvements in this case. It turns out that we've hit some local minima in a few places. this is the best we can do. So while perfect accuracy is not something we can guarantee with this approach, we can get an approximate nearest neighbor graph very, very efficiently. So how do you make all of this fast? Let's start with some algorithm tricks. It's always better to start with algorithms if you can. So the first thing to note is that during the graph construction, we take a lot of length 2 paths to find the neighbor of each and every node in the graph. And this is going to involve a lot of indirection. But we can instead observe that for each common node, any pair of neighbors of that node are neighbors that need to be introduced to each other. And this has the same effect as following all of those length 2 paths. So for each node, we look at all its neighbors and do all the pairwise comparisons between those neighbors. And better still, we can keep track of which introductions of neighbors we've already done, so we don't have to do them again in later iterations. Another catch is going to be hubs, or high-degree nodes, nodes with lots of neighbors. And this will affect both graph construction and search. How do we end up with high-degree nodes when we only connect a node to its k-nearest neighbors? Shouldn't every node have exactly k-neighbors? Well, here's a one nearest neighbor graph with just 4 nodes. And note that the edges here are directed edges. Green has blue as a nearest neighbor, blue has green as a nearest neighbor, and so on. Once we make it an undirected graph, like we were using in the search, we end up with a node where the graph where the center node has 3 neighbors, despite coming from a single nearest neighbor graph. The higher the dimension of the data, the worse this effect can become. And it's actually not at all uncommon to end up with, say, a 15 nearest neighbor graph that has a node with hundreds of neighbors. This is bad when constructing the graph. We need to introduce each pair of neighbors to each other, which gives us a number of neighbors squared introductions to make. And hubs that have a lot of neighbors are going to make that computation blow up. So instead, what we're going to do is cap the number of neighbors we'll look at a time and just sample as many as we need, keeping track of which ones we've sampled and which ones we haven't, so we can try the other ones in a later iteration. On the other hand, when we're doing a search query using the graph, a hub is going to add a lot of candidates to our candidate pool, which all have to be checked and sorted. So to avoid that, we're going to prune away edges from our graph before we actually get around to doing the searching. So if we want to perform a search on the graph, we'll need this one green edge here, because that's going to get us from our green to blue, which are nearest neighbors of each other. It's the shortest edge that can possibly do that. Likewise, we're going to need this edge to get from blue to red. It's the shortest possible path. We need that one. But this edge, we don't need. We can get from green to red by traversing through blue. Now, that's going to add more hops to our search algorithm, but it's going to dramatically cut down on the number of edges if we remove this. So for the search purpose, we're going to remove the longest edges of any of these triangles in the graph. And in fact, we may go further and prune even more aggressively, losing some accuracy in our search, but making it much faster. And one last algorithmic trick that we can play: random projection trees are pretty inaccurate unless you use a lot of them. That was already discussed. But we don't need to be accurate if we just want to get started with this nearest neighbor graph search. So as long as we can do better than random, we're doing well. So a small forest of random projection trees will get graph building off to a good start. And a single tree, and we can pick the best of our small forest, can get the search off to a pretty decent start as well and save a lot of time in search. So how about implementation tricks to try and make this faster? The main trick for making it fast from an implementation point of view was using Numba. So this is a just-in-time compiler for Python code, and it makes numeric code very, very fast indeed. I want to point out that I also actually had a lot of help from the Numba developers, who were always great at answering questions whenever I had them. So I want to thank the entire Numba team. And I do want to share some of the things that I learned along the way about getting the most out of Numba. the first thing you want to do is a lot of profiling to find where the bottlenecks are. There is no point in spending effort on functions that are already fast or don't get called very often. Once you have found the bottlenecks, you can gain a lot of extra performance from writing code in a way that Numba can optimize well and adding type declarations to help Numba out. So here's an example of this. This is an initial version of a Euclidean distance computation. Now, the distance computations are going to be most of the computation in the nearest neighbor search. So getting these fast is really going to matter. When running a benchmark of a whole bunch of nearest neighbor queries using this distance function, it took around 12 seconds to compute nearest neighbors of all those query points. But we can speed things up by adding the fast math decorator to the Numba JIT, and instead of using the NumPy routines, actually writing out all those loops. And that lets Numba do its own optimizations. The result, the same query benchmark now took only 8.5 seconds instead of 12 seconds. That's a big improvement for what is a very small amount of code change. If you're willing to invest more effort, including experimenting with exactly how to write the function, turns out multiplication's faster than squaring, for example, and adding a lot of type information to the decorator, which can really help Numba squeeze out every last bit of performance, we get something like this. This is more complicated, but the end result, we get down to 7.6 seconds on the benchmark. So there is still more performance you can get if you're willing to put in a little more effort and write a little more code. Now, one of the really nice things is that Numba lets you use a lot of standard types, including lists and, for example, the heap queue module for heaps and priority queues. But if you have very specific needs in the very intensive parts of your code, based on all that profiling, I can't emphasize the profiling enough, then custom data structures can help. So, for example, because I needed a very specific subset of heap functionality, it was beneficial to actually write a very custom heap implementation using NumPy primitives and optimize those operations. Now, note, in other cases where I needed heaps or priority queues, I just used the heap queue module because there wasn't a performance difference with Numba for that range of functionality. It's only when I have very specific needs and I can hone in on just those specific cases. But it can really be worthwhile to make your own custom data structures and functions for those if performance really matters. And the last thing I want to mention was a surprise to me, and it took me a while to understand, and many thanks to Stuart Archibald from the Numba team who helped track this down for me. It turns out if you pass a very large NumPy array to a Numba jitted function, it induces quite a lot of function call overhead. And when I say quite a lot, I really mean hardly any. Mostly it doesn't matter. But if you're calling the function a lot, it eventually adds up over many, many calls and can actually slow things down. The solution to this problem is that if the data you're passing around is going to be read-only, and in my case it certainly was, is to write it to compile a closure that references that data. So now the data is not passed in each time to the function, but it's instead compiled into the function itself by Numba. And this removes the function call overhead and caused by the large data being passed. And everything can run a whole lot faster. So if you have functions that are being called an awful lot, especially if they take large NumPy arrays, this is really worth investing some effort in. So how does the result of that compare with other libraries for approximate nearest neighbor search? First, let's look at raw performance in terms of compute time required. And we can make use of the ANN benchmarks library, which lets you run benchmark tests over various data sets. The goal is to compare the entire accuracy query speed trade-off space over various parameter choices for the different algorithms and implementations. And ANN benchmarks lets you do that. It'll provide a curve of the trade-off space between speed and accuracy. And one last thing to note before we look at benchmark plots, PyNNDescent is pure Python, letting Numba do all the performance work, whereas the other implementations we'll be comparing to are all C++ implementations with a thin Python wrapper. So here's our first benchmark dataset in 784 dimensions using Euclidean distance. The comparison is against a number of the best performing approximate nearest neighbor libraries, including Annoy from Spotify, FICE with an HNSW implementation from Facebook Research, and NGT from Yahoo Japan. PyNNDescent is in red, and higher up and to the right is better, and as you can see, it performs very well here. The next data set, this time, it's a very large data set in only 128 dimensions. Again, PyNNDescent is holding up very well. Now let's look at a data set that uses angular distance, this time GloVe word vectors. PyNNDescent is not the best, but it is thoroughly competitive. And another angular distance data set, again, PyNNDescent is highly competitive with other libraries. So some caveats on these benchmarks. Obviously, there will be newer algorithms and implementations improve, so these represent a snapshot in time when I happen to run them. Hardware makes a big difference, so you may see different performance on your hardware than these benchmarks when I ran them. And PyNNDescent doesn't support GPUs, but other libraries, such as FICE, do, and they will have very different GPU-based performance characteristics if you run them. But speaking of specializing to particular cases, another way to compare these libraries is with respect to features. Different libraries are going to target different goals. FICE cares about GPUs, and other libraries care about other things. So what are some of the features that make PyNNDescent stand out? One thing is that it supports a very wide variety of distance measures out of the box. Now, the left-hand column of this list are the ones you might expect: Euclidean, cosine, Hamming, Manhattan, Minkowski. But there are a lot of interesting metrics on the right-hand side that are a lot less common in other nearest neighbor libraries. We support Wasserstein distance out of the box, Hellinger distance, Spearman correlation, Mahalanobis distance, and so on, all out of the box. And there are, in fact, 20 other distance measures not on this list that are, again, supported out of the box. Another benefit is that since Numba JIT compiles things, you can pass your own custom distance metric written in Python, as long as you can Numba compile it. And you can pass that directly to PyNNDescent and use whatever custom distance function you want. If you have some distance measure that you think a lot of other people are going to want to use, please submit a pull request and we can add it as one of the predefined metrics. Another nice feature is support for sparse data in the form of SciPy sparse matrices. You can pass these into PyNNDescent and everything will work largely seamlessly. There is going to be a little care if you want to combine custom distances with sparse data, but other than that, it should work seamlessly. Lastly, PyNNDescent comes equipped with a PyNNDescent transformer class that's a drop-in replacement for sklearn's Neighbours transformer. This lets you replace slow, exact nearest neighbor computations with a very fast approximate one. And due to the plumbing put in place by the sklearn people and how sklearn estimators make use of Neighbours transformers, you can speed up scikit-learn models, including isomap, TSNE, and other things by dropping in PyNNDescent for your nearest neighbor computations. I highly encourage you to see the sklearn docs on the Neighbours transformer or the PyNNDescent docs for more details on exactly how to do this. So, in summary, PyNNDescent is a pure Python library for approximate nearest neighbor search. It's very fast, it's flexible, and it's extensible, and you can install it right now from pip or conda to speed up your existing sklearn workflows. Thank you.
Thank you, Leland, for a great talk. So we have a few questions, and I'm going to go in order with the ones that are uploaded. Okay, let's start with Shannon's question. How do you efficiently identify triangles in the graph? That seems like a hard problem to solve heuristically.
Given that it's a pre-compute step, prior to doing the actual searches, it's pretty much just running through the graph. You can look through and find the triangles fairly efficiently. Triangle finding in graphs is actually not that challenging a problem. As soon as you want cycles longer than length 3, everything gets very, very challenging. But triangles, not so bad.
Okay. And our next question, couldn't you have used Numba function?
Sorry, I lost connection there for a second.
Can you see the question on the screen?
Yes, yeah, that's a fine question. You can use parallel equals true on the Euclidean distance function. And in fact, PyNNDescent makes heavy use of the number parallel equals true. The catch with that Euclidean distance function is that because the function runs so efficiently in such a short period of time, the actual overhead of setting up the parallel threads in Numba is more expensive than the compute time of actually running that. So that's one of those trade-offs. You have to look at where it's going to be worthwhile adding these specific decorators. So you need a function that's going to have a reasonable amount of compute before the parallel equals true is going to be useful.
Thank you. Our next question is from Christopher. Yes. So just to ensure I heard correctly, you were saying directed graphs are used because undirected would...
Actually, no, we convert the graph into an undirected graph before performing the search, which is what generates all those high-degree nodes. If we stayed with a directed graph, things would go a little faster, but it turns out it's hard to find the nearest neighbors on that directed graph. Directed paths are a little more challenging to follow. So yes, we convert to an undirected graph for the search.
Now, our last question is from Kevin. You can create multiple graphs since it's got stochastic, right? Then pick the minimum from the multiple graphs?
Yes, you certainly could. If you want to increase your accuracy significantly, you can do something like that. Create multiple graphs and then pick the best. That's not implemented in PyNNDescent at this time, but I would gladly accept a pull request for that if somebody wants to make one. I'll be available in the lounge later this afternoon if people have more questions. So check the lounge. I'll be at a table sitting there ready to take more questions. So thank you.
Thank you so much. Thank you, Leland. Thank you, everyone, for coming.